My name's John Knickerbocker, and I am a researcher here at TJ Watson Research at IBM. And today we're going to talk about something that's called co-packaged optics. So this is a technology that allows us to go to the next generations of products for future AI applications like AI data centers. And why is that important? The algorithms for training and for inference require lots of compute power. And the compute power has continued to advance and accelerate at a faster rate than the communications of links of sharing that data between chips. What had been done just electrically for multiple GPU modules sitting next to memory chips or HBM stacks has limitations. Optics has been used for decades in communications, and typically it's used something called a glass fiber. And those glass fibers can go very long distances. They can communicate very effectively for low energy, so we can save a lot of energy. We can be able to support very high bandwidth by going to this next generation of interconnection, again called co-packaged optics, where we bring the light directly onto modules and compute modules. We can also drive this further, and we are, to tighter dimensions, so we'll be able to have more and more connections along the edge of a chip. It's called beachfront, and it gives us very high bandwidth density. And we're also able to use one or more colors or one or more lambdas in order to communicate in each of those connections. So not only can we expand and increase the number of channels per beachfront or edge of a chip, but we can also have multiple lambdas, which magnifies this even further. So what we're going to do today is we're going to walk through how we design these things and make the different components. So we design the chips, we design the interconnect links, in this case polymer waveguides. I'm working with a team of people that are in other research labs like in Albany, New York, Tokyo, Japan, and Zurich, Switzerland, as well as up in Canada, Bromont, Canada. And we design the test packages, lids, everything, and we either make or buy those components and work with the suppliers to make this work to meet our technology and future product application needs. So first thing we do is we get the components, and one of the things we do when they arrive is we do inspections. Now, these inspections are typically with very sophisticated tools and in clean room spaces, not in this laboratory, which is a experimental setup laboratory that we can do some ad hoc learning on test vehicles that are not actually going to be built and put in through the full stressing. So in my hand, I've got a little box that usually holds many of the chips that we would be using, and these are called PIC chips, photonic integrated circuit chips. And I'm going to put it under the microscope because they're small and hard to see. And so when I put it under the microscope, then you can see on the screen what the chip looks like. So this is one of the two test vehicle chips that we designed. And on it, if you just look at it, you'll see this area that looks a little bit orange, and what that is an array of solder bumps, and those solder bumps allow us to have electrical connections on and off the chip. In addition, we've got an area, I'll point out here with my finger, which is where the polymer adhesive and polymer waveguide will attach. But on that area, within the chip, there are optical waveguides, and those optical waveguides run, parallel to these two bars that are here, and they would carry the light to the chip or from the chip out and allow us to have that communication link. These waveguides are at a 50 micron pitch. So to give you a perspective of that size, of the distance between these little optical channels, they are on the order 50 microns. So what is that? It doesn't mean a lot to most people. The diameter of your hair is about 7,500 microns. So think about the pitch of these is half the width of your hair. Okay, and so we can put a lot of connections in a short distance, and we're even making that smaller and smaller and putting more and more channels together, or waveguide channels together, so that you can get very, very high bandwidth going on and off chips. We also have these polymer waveguides. So let me see if I can get one of these under the microscope and you can see it. So here is a waveguide. And so think of it like a sheet of paper, only it's made out of plastics, polymer materials. So here are those same matched waveguides at the 50 micron pitch on the polymer that are going to attach to the chip. On this side of this little rectangular square, the waveguides are at this 50 micron pitch, and then they fan out and across the waveguide and go to a coarser pitch. And that allows us to go from the very tight pitch and very high density on chip off to a ferrule, which will have a pluggable connection that allows us to go from the polymer and jump back into the glass fibers, then go very long distance, and that plugs in. Next, we're talking to the steps for assembly and integration of these components that we were just reviewing. So we have here is what's called a thermal compression bonder. There's different types of bonders to assemble components. And so in this tool, this does bonding of the solder of a chip to the package, and you put your sample in, and then we can apply temperature and pressure inside this tool. They come together, join, and then cool down again, and take the package out, and it's now joined. So you got your chip attached to the package. So after the modules have been assembled, as we've talked about, and they get mounted on a test card or board, we want to see that the optical channels are good, have a low insertion loss, and stay good not only through the reflow cycles we were just discussing, but also through JEDEC stress testing. So JEDEC testing is a standardized set of tests that are used in an electronics industry to conform to different types of product applications. So typically the different types of JEDEC tests are representative of trying to ensure high reliability for product form factors. So in electronics, typically there are certain stress test levels that are used for the electronics to survive. In our case, we wanted to show through the right JEDEC testing that not only the electronics can survive, but the optics can also survive all through the fabrication processes and through this harsher stress testing. And that's where we go from minus 40 degrees C, very cold, up to 110 or 125 or 150 degrees C, very hot, and go back and forth. And we do that, hundreds of times, 1,000 times or more to prove that these things can hold together through that thermal shock. And that is typically more harsher than a product would see. And so we want to verify that these things can hold together as a technology before we would use them in a product, so we have a highly reliable product. So what I'm showing you here is this is a test chamber, and you'll see up above the heating chamber and down below the cooling chamber, and we would load samples in here, close it up and program it, and then we would cycle up and down and want to verify that the samples remain good. And so we'd take them out perhaps at 250 cycles, at 500 cycles, at 750, 1,000 cycles to show and measure that the samples remain good. And typically that doesn't happen. When you first build samples, there's defects and failures. So you have to do analysis, diagnostics, understand what's caused the failure, fix it, and then run the tests again. And we've done those tests, they survive, and we're now starting to do product form factors and prototyping to show this technology works in parallel with developing the next generations of technology that'll reduce our energy consumption even further, as well as drive even higher bandwidth density with multiple lambdas and tighter pitch and more channels. So the next thing we do when we have samples is we need to test them and understand the quality of the test. We've done inspections for contamination and particles. We now need to test to make sure the optical channels are good and understand when we do the assemblies if the insertion loss or the losses in the optics are acceptable or not into specification. So this is an optics lab that the team has, and so here on the bench top, we've set up two sets of measurements that could be demonstrated. One is taking our PIC chips and using a microscope and alignment of fiber to bring the light into the test chips, we can hook up and understand the losses going through these channels. The other thing we can do is the little modules that we've been building, those full modules, can be plugged into a little test card and plugged into the glass fibers, and then the light sent in from a laser source, and you'll see here 1310 nanometer coming out, 1 dB, and then it goes through the channel, through the connector, through the polymer waveguide, onto the chip. We have a loop back, so it circles back around and comes back out on another channel. And then we can get from those in and out measurements a reading from the test circuits and understand that channel losses here. And so in this case, we see a measurement of minus 3.6 dBm, and one was in, so we've got 4.6 dBm total, but we're going to the chip and back out. So we can divide that number by 2. So the loss for this total link in this case is 2.3 dB. So that's a typical sample, a good sample, and something we look for at time 0 when we measure after the first assembly. After we go through reflows, we want to see that it stays the same or very similar to our specifications. And when it goes through the JEDEC test stress testing of the different parameters, we also want to see that it's not changing. So this setup and apparatus allow us to do that measurement and characterization. So very exciting, great place to get data, results, and characterize as we optimize this technology for the current test vehicles as well as those that are coming in generation 2 and 3. All right, so thank you very much for coming to our co-packaged optics discussion today. We're happy to have you, and hopefully you've learned a little bit about the work that we're doing at IBM for future applications for AI, data centers, and both IBM and industry partners, customers. If you'd like to learn more, you can subscribe to the channel, and thank you very much.